recording. So today I put together a little slideshow for us. Kind of summing up some of the bigger ideas of modules 14 and 15. Sorry, I'm just moving my Zoom controls all around. I see a question asking if these will be up today. These are taken directly from the notes, so they're already things that are up today. I guess module 15 is not completely up because the slideshow isn't done, and I wanted to post it all together. Oh, I did not click, but it's moving forward. So module 15 will probably be up today. Okay. So module 14, we're not going to spend a lot of time here, but I think we do need to go over the concept of aromaticity, just because that's one of the more challenging concepts in that chapter. So I drew the orbital diagram of benzene here, and I wanted to talk about how the pi electron density of benzene is. So does anyone remember the phrase that I repeated, multiple times talking about the pi electrons of benzene? Where did I say they are? Where is the electron density focused?
Like above and below the ring, right?
Yeah, exactly. Those are the words I'm looking for, above and below. So the pi electron density is, whoops, that was the wrong one, is all above and below the carbon framework. And the reason this is important is because we're about to get into aromatic reactions, and it's important to understand where that electron density is, because that's the source of the electrons that'll initiate the reaction. So remember that the carbon framework of benzene is completely flat. It's all planar. So if you, oh, I guess I drew it in the slideshow. If you were to draw benzene just flat as if you were looking at it from the side, the electron density would be up here and up here. That's also important to aromaticity in general. So only electrons that are in that above and below arrangement are going to be considered for determining whether or not something is aromatic. So those lone pairs that end up out here along the same plane as the actual carbon framework are not going to be considered for aromaticity. So that's why sometimes when you have lone pairs, like multiple lone pairs on a nitrogen or an oxygen atom or something, they are not included in the aromatic arrangement. And we'll talk about that in more detail in a second. So this brings us to Huckel's rule. So a compound is aromatic if all atoms within the cyclic arrangement of atoms have an unhybridized p orbital. So that means that all of those atoms must be sp2 hybridized. The cyclic arrangement of atoms is planar or nearly planar. And this one is one of the harder ones to identify when those compounds start getting really big. So I tend to not ask too many questions about those types of compounds, because you kind of have to see a model of them for some of them in order to know if they're planar or nearly planar. And there are 4n plus 2 pi electrons in the cyclic arrangement of atoms. Are there any questions about the 4n plus 2? I know this one can be kind of tricky because the n, again, does not correspond to anything about the structure. So it's not like you multiply the number of carbons or the number of hydrogen atoms or anything like that. As long as the number of pi electrons can fit into the formula 4n plus 2, you're okay. Okay, so these are the examples that are from the slideshow, and I just want to go back over them again. Oh, I still didn't fix the structure. And I want to talk about why each one is aromatic and make sure that we all understand this. So in our first structure, we have benzene. Does benzene fit the first rule of all atoms must be in the cyclic arrangement must have an unhybridized p orbital?
Yes.
Yes.
Yes. Is benzene planar or nearly planar?
It's planar.
Yeah.
Mm-hmm. And how many pi electrons are in the cyclic arrangement?
3.
Well, there are 3 pi
6.
bonds, right? So there are 2 electrons for every pi bond. So there are 6 pi electrons. Okay, so that's why benzene is aromatic. It fits all 3 of the rules. Let's look at pyridine. So this is pyridine. You've seen this compound before. It's part of the formula for PCC. Do all of the atoms have an unhybridized p orbital in the cyclic arrangement?
Yes.
Yes.
Yes, and I know that nitrogen is kind of the tricky one here because you look at carbon and you're like, well, I know that carbon, when it has one double bond, is sp2, and so that's easy. But remember, sp2 means it has 3 things attached to it. And we have a carbon, and a lone pair. So that's 3 things attached to it. I know that's a severely simplified version of this, but that rule still works here in organic chemistry. If it has 3 things attached to it, it's sp2. So everything has an unhybridized p orbital. Is it planar or nearly planar?
Yes.
Yes, everything is sp2 and it's a 6-membered ring. It's going to be planar. There's no reason that any of those atoms should be out of the plane. And then how many pi electrons are in the cyclic arrangement?
8.
6.
6. Why do we not count the lone pair on nitrogen?
Because it has a double bond attached to it.
Yeah, so because of this double bond attached to nitrogen, that puts the lone pair in the sp2 hybridized orbital. Any electrons that are going to be considered to be part of the aromatic system have to be in an unhybridized p orbital. So this lone pair is perpendicular to the aromatic electron density. So this is that example where your pi electron density of the aromatic system is above and below, but this lone pair is out here. So it is not part of the aromatic system. Does that make sense?
But how can you tell that it's perpendicular? Like, if it's out of the ring, does that automatically mean it's perpendicular?
Not necessarily. It's because this lone pair counts as one of the 3 things attached to nitrogen for its sp2 hybridization. So like if you look at this carbon up here, it has a hydrogen, it has a carbon, and a carbon, right? Those are the 3 things attached to it. And when you guys first learn hybridized orbitals, you talk about 3 things being attached to something, meaning that it's sp2 hybridized. And a thing can be an atom or a lone pair. Nitrogen has carbon, carbon, and a lone pair. So those 3 things are in the sp2 hybridized orbital. So that means that it cannot be in the unhybridized p orbital, which is where we need it to be. So essentially, if the lone pair is one of the 3 things, it cannot be part of the aromatic system. Does that make sense?
Yes, it does. Thank you.
I'm glad, because I didn't know how I was going to say that again in a different way. I think I said the word things about 100 times. Okay, our next structure is naphthalene. And this one is, nice and simple, but sometimes students get a little tripped up by those single bonds coming off of benzene, which is why I included it here. When you're looking at naphthalene, you have to determine if every single carbon atom is sp2 hybridized. So you can kind of look at this and say, well, that looks just like benzene. So I know that all of those are sp2 hybridized. Are these two carbon atoms sp2 hybridized?
Yes.
Yes. And what about these two?
Yes.
Yes.
Yes. So all of these are sp2 hybridized. Is this going to be planar or nearly planar then?
Yeah.
Yes. And how many pi electrons are in the cyclic arrangement of the unhybridized p orbitals?
10.
Right. So there's 2 for every pi bond. So that gives us 10, and 10 fits the 4n plus 2 rule. Okay, so this next one is furan. And this one's a little trickier. Do you guys remember why? Why is this one kind of tricky?
Because the
We only
doubles.
count one. We only count one pair of electrons from the oxygen and not the other.
Right. And because one of these pairs can be in resonance, that kind of changes the hybridization of the oxygen here. Even though it should be sp3 hybridized, it's kind of not because of the resonance form that can be created. And so that makes oxygen kind of weird here. Okay, so let's go through our checklist then. Is every atom in the cyclic arrangement, we're not going to ask if it's sp2. Let's ask instead, does every atom have an unhybridized p orbital?
Yes.
Yes, there has to be, otherwise there wouldn't be resonance here. Is this molecule planar or nearly planar?
Yes.
Yeah.
Yes. And then how many pi electrons are in the unhybridized p orbital?
6.
6, right. We're going to use the pair that's in resonance, the electrons that are in the actual pi bonds, but not this one. So remember that that extra one, if you draw furan on its side, which I think actually might be the next slide, so I'm probably doing a little extra work here. We have our electrons here, 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 and here. And then we have a pair here and a pair here in the hybridized orbital. So these are not part of the above and below arrangement. They're just off to the side. Okay, let's look at cyclopentadiene. Does every atom have an unhybridized p orbital?
No.
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 All right, this is sp3 hybridized. Is this going to be planar or nearly planar?
Yes.
Yeah, it's probably kind of close to planar, but since this is sp3, at best it's nearly planar. We can skip answering that one if we want to. Without seeing a model, that can be kind of difficult. I'd say it's probably nearly. And then how many electrons do we have in our unhybridized p orbitals?
4.
4. So this does not follow Huckel's rule here. Is this compound anti-aromatic?
It's not aromatic.
Right, it's non-aromatic. Why is it non-aromatic instead of anti-aromatic?
Isn't the 4 pi? It follows 4 pi. Not. It doesn't follow either of it. Either.
Well, it follows. Well, since this is 4, that would be 4 times 1. So it does have the right number of electrons to be anti-aromatic. But what does it not have?
It's not all sp2 hybridized.
Right. So
Yeah.
having this sp3 carbon in here prevents it from being anti-aromatic. Okay.
I have a question. I'm sorry. When I was trying to do it by myself, I thought it was how is it sp3? Like I'm confused.
Because there are 2 hydrogens here. Because there are no double bonds to that carbon, this carbon has 4 things attached to it.
Oh, okay. Thank you.
Okay, so the next one, we have a cyclopentadienyl carbanion. Is this one planar, or sorry, the first question is, does it have an unhybridized p orbital on every atom in the cyclic arrangement?
Yes.
Yes.
Yes. We learned in a previous chapter that carbanions are sp2 hybridized. So is this going to be planar or nearly planar?
Yes.
Yes. And how many electrons are in the cyclic arrangement?
6.
6.
Right. So we count this one, these, and these, because they would be in an unhybridized p orbital. Okay, and then last one, is this going to have an unhybridized p orbital on every atom in the cyclic arrangement?
No.
Yes.
Yes, it does, because carbocations are also sp2 hybridized. Will it be planar or nearly planar?
Yes.
And then our last question, how many pi electrons do we have here in the cyclic arrangement?
2.
2. Right, so with the 4n plus 2 rule, n would equal 0 here. So this is aromatic. Okay, does that help with aromaticity a little bit, being able to go through these again? Okay.
Yeah.
Yes.
Or were we good on it already and I wasted time?
No, it clarified between not aromatic and the anti-aromatic for me.
Okay, good. Let me go ahead and put this up here then. We don't have to go through all these examples because we just did a whole bunch of these. But the aromatic and anti-aromatic thing, remember that anti-aromatic means it fits those first 2 rules, but it has the wrong number of pi electrons. I saw a question from Allison asking, could you explain what we mean by nearly planar? So nearly planar means that it might have like, a small buckle in it or something, but for the most part, the atoms in the cyclic arrangement are in the same plane. This is mainly to help with some of your larger compounds, like if you had, why did I pick this? Now I have to try and come up with an aromatic structure. Okay, let's look at this one real fast. This has 7 carbons and a carbanion. This is not one of the examples we've seen so far, but this one's kind of tricky. We have 7 carbon atoms, so it's unlikely that this would be perfectly planar, but it probably is nearly planar. And what we mean by nearly planar is like this bond here might have a small buckle in it. So it might not just be perfectly in the plane. So we're talking about a difference between, having something kind of out of plane and like cyclopentane, which has like a true fold in it in the envelope conformation. So as long as you could see it being planar, it probably is. Where you start having some issues would be like when you have a 10-membered annuline, or this one actually is planar, but there are some examples in your homework where you have these large annulines and you don't have the alternating trans, cis, trans. So it goes like trans, cis, trans, trans, cis, trans, cis. Having that alternating arrangement like that, for the most part, gives you something that's likely to be planar. If you could actually see, the benzene rings within it, it's most likely to be planar. I know this sounds kind of like waffling as far as like an answer, and that's because it kind of is. There aren't like really any set rules here because there are so many possibilities. For the most part, when I give you guys a question and I ask you if it's aromatic or anti-aromatic, you'll know if it's planar or not. I'm not going to ask you something really tricky, because for a lot of these, you'd have to draw a model in order to actually know the answer. And I just don't expect that from my Organic 2 students. Like if I would have to draw, or if I would have to create a model in order to answer it, I'm not going to ask you. Does that help?
Yes, ma'am. Thank you.
Maybe more the prompt of not making the question difficult is better than actually fully explaining. But if you're not sure, you can always, use an online modeling site to see what that structure looks like. But let's go through the rest of the questions for this one since we're already here. I do think this would be probably planar or nearly planar. Are all atoms sp2 hybridized or have an unhybridized p orbital?
Yes.
Yes. How many pi electrons are in the cyclic arrangement?
8.
Yeah, there are 8. So we have 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 pi electrons. Is this going to be aromatic or anti-aromatic or non-aromatic?
It'd be anti-aromatic.
Yeah, this would be anti, because it fits those first 2 rules, but it has 4 pi electrons instead of 4 in pi electrons rather than 4n plus 2 pi electrons. So that's the only difference between aromatic and anti-aromatic. Okay, so the next thing that I want to discuss with you guys is electrophilic aromatic substitution. And we're just going to get started on this basically. I did post some videos about electrophilic aromatic substitution last night. The rest of them I hope to post today and tomorrow. But also labs started today and I'm going to be on campus all day today. And it has already been an interesting morning. So I'm not sure I'm going to get as much done during the day as I thought I would, but I will try. So with electrophilic aromatic substitution, the key thing here is that your benzene pi electrons are going to act as a nucleophile, and they're going to attack your electrophile, which is formed in the reaction mixture from your reagents that you're using. And then ultimately, you still end up with something that is aromatic, but you've subbed out a hydrogen atom for something else. So that's why this is considered a substitution. Just like SN1 and SN2, you subbed out your leaving group for your nucleophile. This is a substitution, not an addition. And the reason I'm harping on this is that all the other reactions that you've seen with alkenes are actually additions to the alkene. So this is different because you're going to keep your double bond. Even after using it as a nucleophile, you're still going to end up with that double bond there. So our 5 main types of reactions, we have halogenation, which is the replacement of a hydrogen atom with a halogen atom. Nitration, which is replacing a hydrogen atom with a nitro group. Sulfonation, which is adding a sulfonic acid group. This is a Friedel-Crafts alkylation. So alkylation is the general type of reaction here. The main one that we'll look at is Friedel-Crafts, but there is an alternate alkylation as well. And then Friedel-Crafts acylation. So when you see aluminum chloride being used, that means that it's a Friedel-Crafts reaction. The other thing that I wanted to point out, I mentioned this in my video, but I want to mention it to you guys in class as well. The group that's actually being added to the benzene ring is probably the place where people make the most mistakes. So notice that the nitro group, NO2, varies from the acid that it comes from by 1 hydrogen atom and 1 oxygen atom. So you take away the hydrogen, you take away 1 oxygen, and you get NO2. Your sulfonation comes from sulfuric acid, If you take away one hydrogen atom and one oxygen atom, you get the sulfonic acid group. Students always end up putting on like SO4H or SO3H2 or NO3 or something like that. Know what your groups are. It's pretty simple. You just have to take away one hydrogen and one oxygen from the acid. The other things that students get confused about, sulfonation uses sulfuric acid and sulfur trioxide. You can also do this with just concentrated sulfuric acid. But nitration involves nitric acid and sulfuric acid. So if I were you, I would create some flashcards that have all of these reactions on it just to help keep those reagents straight in your head. You're not going to be able to learn Friedel-Crafts alkylation by flashcard, but your flashcarding can help you recognize that when you have an alkyl halide and aluminum chloride, that you're going to be adding on an R group to your benzene ring. So use flashcards to help you recognize these reagents and then make sure that you understand how these reactions actually work. So there is a generalized mechanism for electrophilic aromatic substitution that all of the electrophilic aromatic substitution reactions use. The first step is to form the electrophile. And this is the step where you have a lot of variation between all the different types of reactions. You have a bunch of different reagents that you're starting off with, and you're going to end up with a bunch of different electrophiles. Although they all tend to start with a Lewis acid, Lewis base interaction. And then once you've created the electrophile, they all get back on track again, and you have a pi attack of the electrophile. So the pi electrons of benzene are going to attack the electrophile. And then you deprotonate. Whoops, I forgot to edit this one. I edited the one that I used in the video. Deprotonate to reform the aromaticity of the benzene ring. So I'm going to draw out an example here. We're going to start at step 2. So assuming that we've already created our electrophile. You have your benzene ring. You have your electrophile. The electrons from benzene reach out and attack the electrophile. This should remind you very, very much of the addition to an alkene. So if we put the electrophile here, there's also a hydrogen atom here. There's a hydrogen atom here as well. What else needs to be on this structure right now?
Isn't it a carbocation?
Charge?
Yeah. So we used these electrons in the pi bond to create a new bond to the electrophile, right? So those are here. That puts a carbocation on the other carbon. The most common mistake that I see in this mechanism is students will draw this. They put the carbocation on the same atom as the electrophile. That doesn't make any sense because the electrons are all on that carbon, right? It's this carbon that lost electrons, and therefore it's that carbon that ends up being a carbocation. Okay, so that's step 2. And then in step 3, we deprotonate to reform the aromaticity. So your base comes along, and your base is also formed in step 1. So it'll vary with the reaction as well. Where do I deprotonate from? I'm going to call this proton A and proton B. Which proton am I going to deprotonate?
Is it B?
A.
I thought you had to reform back.
Let's
the
go
B
ahead and
hydrogen.
let's vote by chat. This will be your attendance for the day. In the chat, just send A or B, and you can send it to the entire class if you want, just A or B, or you can text just me. Just type A or B.
What's the question?
Which proton are we going to pull off, A or B? Okay, so the A's definitely have it. That's majority A answers for sure. I only see a handful of B. A is the correct one. So remember, the carbon that has proton B on it is already lacking electrons. We're not going to take away more at this point. We're not going to take away anything from that carbon. So we're going to pull off this proton. And when we do that, the electrons in this bond move towards the carbocation. And the other way that you can kind of see this in the structure is that in your final product, you're still going to have a hydrogen here, but there's not a hydrogen here. If there were, this carbon would have 5 bonds, and we learned in OChem 1 that that's like the greatest sin of organic chemistry, right? We do not put 5 bonds to a carbon. So this is our final product. So we know that we have to pull off this hydrogen because it is not in our final product. Does that make sense so far?
Yes.
Okay, so we're going to do some practice problems in a bit, but the next challenging part of this chapter is actually the directing groups. So when you watch the videos later, you'll see that I take you through the formation of all the electrophiles, and if we have time, we can work on that a little bit today. But it's really pretty straightforward. So the next thing that I want to show you guys is the directing groups. So directing groups basically mean that if something is already on the benzene, so all the reactions that we've done so far were just with plain old benzene, right? No substitutions on it, nothing exciting. But if you have something like toluene, something that already has a substituent on it, and you put it into these reaction conditions, a reaction is still going to occur. But the group that is already on the benzene ring is going to tell you where your next substitution can go. So they're kind of like a traffic cop, like standing in the intersection and saying, you can go right, you can go straight, you can go left, or whatever. Like if you've ever gone to a concert and you have like the parking attendants like telling you, you can go here, you can go here, and you can go here. And, you know, inevitably you're always in the line that ends up like having to park as far away as possible, right? But that's what a directing group does. So depending on the properties of the directing group, you're either going to end up with a mixture of ortho and para products as pictured above, or you're going to end up with a meta product. So ortho para directors go together. If it directs ortho, it's also kind of directing para, and we'll talk about why in a little bit. And then meta is on its own. So some groups are meta directors. You're only going to end up with meta products. Does that make sense? So when you do these reactions, you're looking at what is already on the benzene ring, and that stays there. It is not affected by the reaction. And what it says is, if I'm doing, let's say I do a nitration, then since this is a meta director, my nitro group can only go in the meta position. So that's what we mean by director. It's telling you where the next thing can go. Okay, so let's talk about what ortho-para directors look like. Ortho-para directors will all have a lone pair on the atom attached to benzene, or they're alkyl or aryl. And they are all activating, meaning that they make the benzene more reactive. So if you have an orthopara director on the benzene, you may not have to heat a reaction that normally would require heat because the benzene is now more reactive. We're going to go over why in a second, but I want to look at what some of these examples are. So they have a lone pair or they're alkyl aryl. So your alkyl and aryl examples include things like toluene. Toluene is going to be activated, and it's also going to be an orthopara director. So if you take toluene and you react it under nitration conditions, which is apparently my favorite reaction today, because it's the only one I can think of, you're going to end up with a mixture of the ortho product and the para product, because toluene is an orthopara director. The lone pair thing, what we mean is the atom that is directly attached to benzene has to have at least one lone pair. So in this case, we're talking about the oxygen that's part of the ester here. This would be an orthopara director, and it would also be activated. However, if you draw an ester, with the carbonyl attached to benzene, is this going to be an orthopara director? Does this fit the rule?
No.
No, why not?
The carbon doesn't have like the lone pair of electrons that's connecting directly to the.
Right, so when we're considering this rule, we're only concerned with the atom that is directly attached to benzene. And in this example, we have a carbonyl directly attached to benzene, the carbonyl carbon. It does not have a lone pair. So this is not going to be an orthopara director. This is actually going to be a meta director. And we'll talk about the properties of meta directors in a second. But your types of orthopara directors, I used to give a list to students, but then they tried to memorize it, and I think that's useless. But some common examples include like phenol, aniline. These are all orthopara directors because they have that lone pair directly attached to benzene. And then don't forget alkyl and aryl. Those tend to be confusing for people. The other bit of this rule here is that halogens are orthopara directors, but they're not activating. They're actually deactivating. So a benzene with a halogen on it, even though the halogen is orthopara directing, it's actually going to make the benzene less reactive. We'll talk about why in a second. Does this make sense so far? We recognize how to spot an orthopara director.
Yes.
Cool, thank you. So meta directors have a positive charge or a partial positive charge on the atom directly attached to benzene. Meta directors are electron withdrawing and are deactivating. So examples of meta directors include the nitro group. So the nitro group, people often forget the structure of this, but the nitro group actually has a positive charge on the nitrogen. So you have a negative charge on one of the oxygens and a positive on the nitrogen. That makes it a meta director because you have that positive charge on the atom directly attached to benzene. That's also why anything that has a carbonyl, if it's attached to the benzene by the carbonyl carbon, we know from previous chapters that that carbon has a partial positive and the oxygen has a partial negative. That means that the atom directly attached to benzene is partially positive. So that's going to make it a meta director. Does that make sense?
Yes.
Cool. So In this example here, I drew out several different products. We have a nitro group, and we are doing a nitration reaction. I drew the ortho product, the meta product, and the para product. Which product is our major product?
Meta.
Right. So this is our major product. Does that mean that none of these products form?
No.
No,
but
it does not
mostly
necessarily
makes
mean that
better.
none of those form, but you're going to get very small amounts of those products. So a lot of this is focusing on the major product. For some of these reactions, we'll talk about like this one is only going to give you this product. You're going to see like less than 1% of the alternate product or whatever. But for most reactions from here on out in OCHEM, you're going to see that like a lot of products can be formed in these reactions. They're not very straightforward as far as that goes. So your questions will always be phrased as, what is the major product? So in order to see why, you have to look at the resonance structures in the reactive intermediates, and that's actually something that I put into the videos. So you can watch those videos and just have all the fun with resonance forms that you want. Okay, so I gave you guys these 3 practice problems here, and I actually already did this one with you on accident. But I want to go through these together. So this top one, we have toluene, and it's going through a nitration reaction. Is the methyl group ortho-para directing or meta directing?
Meta.
Ortho-para.
Ortho-para.
Yeah, it's an ortho-para director. So remember that ortho-para has either a lone pair directly attached to the benzene ring, or it's an alkyl aryl group. And then what does our substituent that we're going to be putting on the benzene ring look like?
NO2.
Right. So for this one, if I asked you for the major products, I would want you to draw both the ortho and the para. And later we'll talk about how in some situations you can actually determine whether ortho or para is preferable. We'll work on that more on Friday after you guys have watched the videos. Okay, our next reagent, this is acetophenone. Is this going to be an ortho-para director or a meta director?
Meta.
Meta, right, because it has a partial positive on that carbon. So go ahead and just take a second and draw out what you think the product would be. Okay, so what substituent are we putting onto the benzene ring?
BR.
BR. Okay, and I'm going to label some carbons. Which carbon are we putting it onto?
B.
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 B, right? We're putting it into the meta position. Okay, the next one is a little trickier. We actually did not talk about this yet today. Whoops, okay, hold off on that one. We'll do this one on Friday. We didn't talk too much about activating and deactivating and how it affects other reactions. Although we have 4 minutes, so you know what, never mind. Let's just do this together. We have 4 minutes left. So we have a nitro group. Is this ortho-para directing or meta directing?
Meta.
Meta, right. Okay, so remember that meta directors are also deactivating. So in order to get a nitration reaction to occur, we would have to heat this up. significantly. We're going to go ahead and pretend that heat was already on there. And our product after step 1 would be the meta outcome of this. Now, we've now added 2 deactivating reagents onto this ring. Did anybody get far enough into the chapter to know anything about how that affects Friedel-Crafts reactions?
No.
No? Okay. So Friedel-Crafts reactions need to have an activated benzene ring or just plain benzene. Once you put a deactivating substituent on there, Friedel-Crafts is unlikely to happen. Since we've put 2 on there, Friedel-Crafts is definitely not going to happen. So this would actually be your final product here. After step 2, nothing else would happen. And that does seem like a trick question. It kind of is, but you will see that on your quizzes and on your exams. A situation where there is a no reaction due to activating and deactivating. It's kind of a cheap way of asking you, is this activated or deactivated? Does that make sense? There's actually an entire video called Limitations of Friedel-Crafts Reactions that you guys are going to get today, hopefully.
Cool.
Let's see what else I put on here. I want to talk about, we'll go to this one on Friday. I want to talk about Friedel-Crafts. Whoops. Okay. So in the Friedel-Crafts alkylation of benzene, I did actually create a video about this for you guys, but I want to talk about this with you in person real fast. So let's say that the reaction you're given has aluminum chloride like it should, and then has 1-chlorobutane. Did anybody watch the video on this and know how this reaction starts?
No.
Okay. So I know I posted the video last night, but I also asked you guys to read a little bit over the weekend. Today it's not a big deal. In the future, it's going to be kind of a problem. So the first thing that we're going to see is a Lewis acid, Lewis base interaction. We have a ton of electron density on this chlorine atom, and we have a partial positive on aluminum, partial negatives on all of these chlorine atoms. So we end up with a Lewis acid, Lewis base interaction. And that gives us this kind of weird complex that actually has a negative charge on aluminum and a positive charge on chlorine. Does chlorine like being positively charged?
No.
No.
No, chlorine is an electronegative atom. It's going to be very displeased by this arrangement. And so what happens is the bond breaks and you end up creating a carbocation. Now let's take a look at this carbocation. Is this a good carbocation?
No.
No.
No, this is really bad, right? This is a primary one. Marlena actually wrote in what we need to do here. We need to do a hydride shift. We want to take this primary carbocation and make it secondary. So the reason that this is important is that this is actually the electrophile that benzene is going to attack. So instead of adding on a straight chain, like you might think you would, looking at your original structure here, you're going to end up with this product. Now, this just involves you knowing what the carbocation looks like and figuring out if it's going to rearrange. So that's a common quiz question as well, is I give you an alkyl group that is primary or is going to create a secondary carbocation. where a more stable one is possible, and you need to recognize that rearrangement. So that's something that we will work on more on Friday. We're actually out of time, so I'm gonna let you guys go. I also have office hours today at 12:30. Matthew asked if this is concerted. It depends on where you read, honestly. Some textbooks teach it as the carbocation actually forms. I think that this bond would kind of break as this carbon, I think this bond would kind of break as the hydride is shifting over. I think it would kind of happen all at once because a primary carbocation is kind of unlikely to form. Yeah, it really does depend on the textbook that you read. Some of them like to simplify it to the primary carbocation, and I'm honestly fine with that because it makes it easier for you guys to recognize what's going to happen. Okay, yeah, I have office hours at 12:30 today. So the Zoom links are up on Canvas. Any questions before I go?